So what we did here, we used gprof. This is one example profiler. To use gprof, what you have to do is you compile the program, but you specify the -pg flags shown here in this line. This is the one line that's not counted, this line here. So this is the program, you say -pg for profiling. And then you run the program quite normally. Okay. And so in this case, like with run Dominator, that produces a file with data that record the execution of that program. So what happens in profiling is that the compiler, when it creates the executable, will actually create an executable that records whenever another function is called. And in addition, it uses statistical sampling, whereby every so often it stops and says, where am I? And looks at where it's currently executing. So statistical sampling. The program could record every single branch, but that would be too expensive, therefore we do it statistically. This information is collected here, and then you run a gprof program that then analyzes this information. So I did this here, and the output of that, and of course I run this on the small sample that finishes. Okay, the large one doesn't, the small one does. So I ran this here, and this is the output that I'm getting. I want to show you how to use this output to track down the source of the problem. Okay, so first of all, what do I find? The output gives me a profile of the different functions in this program. Unfortunately, this is C++, so the functions are rather hard to read. But nevertheless, I see that 48.5% of the time is spent in this function, and 11% of the time was spent in this, and a small percentage was spent in this time. So whatever is wrong with this program, it must have to do with this function in some way. Okay. So what is that function? It's a function that's called distance. Okay, this function. And the other ones are operator plus plus and operator not equal to. Remember, in C++, operators are like functions, and I mentioned earlier C++ is compiled down to normal symbols. So as far as gprof is concerned, that's just a function with a really weird name. Okay, so now we need to identify who's calling this function, and such that this much time is being spent in here. So what's being recorded here is that 48% of the time is spent in this function or functions called by it, and there are 2,690 calls to that function. The gprof output contains two parts. At the top is the so-called flat profile. This is simply sorted by largest to smallest, what function did we spend time in. The second part of the gprof output gives us the dynamic call graph. I'll show you this dynamic call graph. So if you think of a call graph like this, in other words, if you have a caller that calls a function, let's say this function in the center, this function will be called by multiple callers, caller 1 and caller 2. Caller 1 called this function, later on caller 2 called this function. Then within that function may itself have called other functions, callee 1, 2, or 3. You know, during one call we have called callee 1, the next call, callee 1 and 2. This is the summary information. It says during that run, from this function we saw calls to these functions. Okay, so imagine a call graph as consisting of connections between functions in this way. So here, this is in the excerpt, a small section of the call graph that looks at the callers and the callees of a given function. And gprof outputs the call graph by giving you, for each function, its callers and its callees. So keep that in mind. In fact, the callers are above the line, the callees are below the line. So we need to look in the call graph output, which starts below here, call graph here. We need to look at this. An example is shown here. This says the main function called load graph, graph constructor, and another function excellent signal that I put in here. In fact, this is the main function. It called excellent signal. It called the graph constructor here, and it called load graph. That's correct. We did this in each of the invocations of main, it called that, and so on. In main itself, there was no caller that could be identified, and gprof records that as, it looks like there was a spontaneous call to main. Okay, because gprof doesn't profile that. So let's look at the culprit, okay, which is the underscore distance function. All right. So I'm searching, I'm using VI to search for this, and I found it right here. So this is the section of interest. This is a bit difficult to see. Section of interest. This is the line that corresponds to the function that we're looking at. Okay, this is the underscore distance function. And we're seeing two things here. We're seeing that there were 2,690 calls, and that there was a huge number of calls, 7792 and so on, calls to the plus operator, and also a large number of calls to the not equal operator. And on top of that, in this chain, 64%, 64.3% of the time was spent in that function or functions called by it. Okay, so that's that. So this is here. It sums up the time spent. Okay, so clearly this is where the majority of the program is being spent. Now, where is this function being called from? It is being called. It has only one caller. So all 2,690 calls to it came from this caller. Look at what is this function. Now this was the function, it was underscore distance, and maybe unsurprisingly it is called from just distance. Okay? So now we need to look for where distance is being called, and where distance is being called from. And we see this is the next block here. This is the block of interest, is this part here. We see distance, which is this one. It has one caller up here. All 2,690 calls to distance came from here. And then it called itself, it called the underscore distance, also calls another function. Okay, so the call came from here. Okay, what's that function? That's a function called size. Alright? Okay, so where is that function described? Size function is here. Okay? So let's look at this entry, and this is where things get a little bit hairy, but this is the function that called it. Okay, wow. So the function that, this is down here, this is a size function. It called these functions that we're interested in, but it had only one caller, which is this function here. Okay, so this is a boost function, and it is fully templated in all its glory. Now this is where I wish I would have some pretty printer, and I'm going to write one if I can find one online. So what is that function? That function happens to be called num vertices, because you wouldn't see that. If you look closely, okay, this is the function. Okay, so it's a function called num vertices, okay, heavily templated, that calls size. Now this function here, by the way, is a standard list, STL list, and the size function is being called. It's called from num vertices. And by the way, so we look at, this is a list, okay, and its size function is being called. That resulted in calls to distance, to underscore distance, resulted in calls to the plus operator, and resulted in calls to the not equal operator. Want to guess why that is?
List is linked list.
List is linked list, and?
There's no size of the linked list. You have to traverse the whole thing.
That's right, okay. So in fact, there's a loop that traversed over that list. And I don't have that.